Okay, hello everyone. This is supposed to be the first quick tutorial on how to use Abaqus it's a simulation software. Basically, you could use it for mechanical simulation, fluid simulation, thermal simulations, and some other simulations. The focus today is to do the simplest simulation for mechanical load, just a tensile load. So I'll just draw a simple rectangular shape geometry and load it. So first, this is how the software looks when you load it by default. You just need to follow this menu, which has part, property, assembly, steps, and all this stuff. I'm going to go through most of them that we need for this quick tutorial. So first, you need to have a geometry, which you start by creating a part. This part could have different definitions, but the default is the basic and most practical common one. We just need to rename the part and just for today call it test 1. It's going to be a deformable object, and it's going to be a solid. And the way I'm going to draw this geometry is through an extrusion. So I need to draw a cross section and extrude this cross section to get a rectangular prism geometry. So I need to click continue, and then I'll get this grid as a reference. I'll select the rectangle here from the draw menu and draw a basic rectangle. By default, there are no dimensions, so you need to assign dimensions by adding a dimension. And here I'll put 10 millimeters for the width. Click enter. And again, maybe 15, so just wouldn't be a symmetric part. And then by clicking the middle button in the mouse, you move in the bottom, you can see here the sketch is done, so now I can click next to go to an extrusion. And this geometry, I want it to be a long geometry, so I'll give it a height relative to the width, which is 1015. I'll give it a height of a 50. And now you can see I just got this geometry. I have to clarify that in Abaqus there are no units, so the geometry you draw based on the other variables you put in should follow that unit. So assuming I draw this part in millimeters, then all the other values, for example, for material property, like the tensile strength or the modulus of elasticity, you should plot that using the same unit. So here it's millimeter, and then I'll plot that with millimeter ratio. So to continue from here, I got this geometry. Was an easy step. It's a simple geometry, but you could also import other geometries that you did on a different software. For example, SolidWorks. Other CAD softwares allow you to do more complicated geometries, and it's easy to just import them here to Abaqus. The next step would be to assign a material for this geometry. So it's in the properties, and it's the first icon. So create a material, and you could give this material a name. For this test, just call it Aaluminum. Okay, and it's usually there's no by default a library in Abaqus for material. So you have to assign the material properties manually. You can save this material and use it later, but the first time you use it, it has to be manually entered. So you can start by putting in the density of material. Usually this is required for a dynamic simulation, something that has inertia, a motion, falling item, or anything. So by default, I'll just put the density of what aluminum density should be. So just put a random number now. It's not very sensitive what we're doing, but the unit has to be, because we're using millimeters, so it has to be kilograms in millimeters, which puts it at a 2 and an E minus 6. So I'm just changing the volume to E minus 9 actually to per millimeter cube rather than meter cube. So these are kilograms per millimeter cube, which is a 2.09. Mechanical properties, for what I'm trying to do here, I'm trying to just load this part and tension. So I'll just put in mechanical properties only the elasticity. You can later add plasticity, but just to do this as simple as possible, I'll just add elasticity. And the default elasticity is isotropic, so in all directions the part is supposed to deform in a symmetric way. And you only need to put 2 values. So the Young's modulus of aluminum, which is 70, it's usually a 70 GPa, but again, because this is millimeters, so it's the values are going to change. We're not working in Pascal per meter square. We're working in a Pascal per millimeter square, which would be a million times less. So which leaves us, hopefully, if I'm not wrong, with 70,000 instead of 70 billion. So, and the Poisson's ratio is a regular, almost common number for metals. It's usually around 0.3. So I'll just put this number for this test. And here, if I click OK, I've defined the material. And I can click here to check what I've already have. So in the material manager, you can see that I already have now aluminum, which I already defined properties. And if I click edit, I can go back and change those properties or add other properties. The next step, after you define the material, so this is in material manager as a library, I have a material, but I didn't tell the software that this material is for this part. So to do that, you have to create a section, which is a definition of the geometry. That the simplest way to say this is to connect the material to the geometry. So I create a section, I call it the aluminum section, so alum sec as a default name, and a default properties of it's a solid homogeneous. As I said, you want it to deform in homogeneous ways. I'll just say continue, and this would be my first material assigned to this section. So the alum sec is going to be connected to the aluminum material. But this creates a geometrical approach to connect the material. The next phase is to confirm that this connection, I want it to be for this geometry. And to do this, it's in the third step, which is assign the section. So I want to give this section to this material, and I click done. As easy as that. Asks again which section. I only have one option now. So again, of course, it's aluminum sec. And when I click OK, the color of the pot changes to a color between green and blue, depends on your screen. And this means that this part, this geometry, has aluminum material defined for it. The rest of the options are a bit more advanced options that you won't use for basic simulation. This is one is for, like, for example, for composite layups, so, and other stuff, so I won't go into those. So now we have a part with a geometry and a material assigned. Now I need to put it into the setup for the simulation, which is the assembly. So this is not like the CAD softwares, and assembly is not a place where I'm supposed to build several parts. I can do that. But the point of the assembly in simulation is this is the workplace where I'll put the loads, I'll fix the part, and I'll do other stuff to get the simulation. So the first step is to create the instance, which means insert the geometry with the assigned material. And the default is the only one we have here. So we're supposed to have a list, but we only have this, test one. So I'll click OK. And here we have the part in the assembly. There is no need to do anything else, but options are, for example, do linear pattern if there's a repetition of the same part, and other options that no need to go into details now. Then what you need to do is to specify what kind of loading you want to do on this part, so or what kind of simulation it is. So in this step is where you choose the type of simulation and you create this step. There's the initial step where there's nothing happening to the part yet. And here you have the list of the steps. Always the default for such a load, just a tensile load, which is kind of a static deformation. You use the static general. It's always default. And you can better rename it the step here, and you can call it alum load, for example. And then you just continue, and you get the settings for that simulation. Again, default is always okay, except one value, which is if you go into basics, the time increment, the total time for the simulation is going to be 1 second of deformation. And it's very simple, so you don't need to do additional stabilization or dynamic stabilization or whatever. But in the incrementation, so these are the steps of the simulation, and the calculation will be divided into steps. So if your initial increment size is 1 and your total time is 1, then the whole thing would be 1 step. And this is usually not a good option because it results in errors and inaccurate results. So you always better reduce this initial step. For a simple case, just 1/10 of the total time. And this should be the maximum step possible. But the software will initiate with this one. And if there are errors in this, it will switch to a shorter time to try to get to results, and it will keep switching to shorter times until it gets to this value. And if it gets to this value and still no